Modules and Homological Algebra, Lecture 13, Categories and Functors. We start with the definition of a category. Definition: a locally small category C consists of the following pieces of data. First of all, we have a class of objects, which is usually denoted by C. Then, for each objects I and j in C, we have the set Cij of morphisms from I to j. Then, for each object I in C, we have a fixed element 1i, which is a morphism from I to I. And finally, for all I, j, and k in C, we have a map, the composition map, from Cjk times Cij to Cik. Also, briefly about the terminology, the morphism 1i is called the identity morphism at the object I, and the map circ is called the composition. So this is a composition of morphisms in the category. Please note that the set Cij might be empty. Of course, if I is not equal to j. Cii is never empty because it contains the identity morphism at I. So this is a datum which describes a category C, and this datum is supposed to satisfy the following axioms. First of all, composition should be associative. This means that for all objects I, j, k, and m in C, for all morphisms f from I to j, for all morphisms g from j to k, and for all morphisms h from k to m, the following identity must hold. If we compose the composition of h and g with f, the outcome should be the same as if composing h with the composition of g after f. This is the first axiom, and the second axiom is the unitality of identity elements. This means that for all objects I and j in C, and for all morphisms f from I to j, the following identity must hold. F must be equal to the composition of f after the identity at I, and similarly f should be equal to the composition of the identity at j after f. Here are some examples. Example 1, we have the category sets, which has sets as objects, maps between sets, or alternatively we call them functions, as morphisms, identity maps as identity morphisms, and composition of maps as composition in this category. Example 2, we have the category groups, which has groups as objects, group homomorphisms as morphisms, identity homomorphisms as identity morphisms, and composition of homomorphisms as composition of morphisms. Example 3, we have the category top of topological spaces, which has as objects all topological spaces, as morphisms continuous maps between topological spaces, as the identity morphisms the identity maps on topological spaces, and as composition of morphisms the usual composition of maps. Here are some further examples. Similarly to groups, we have the category of rings, which has rings as objects, ring homomorphisms as morphisms, identity homomorphisms as identity morphisms, and composition of homomorphisms as composition of morphisms. Example 5, we have the very important category AB, the category of abelian groups, which has abelian groups as objects, and then group homomorphisms as morphisms, identity homomorphisms as identity morphisms, and composition of homomorphisms as composition of morphisms. And our last example is the category of all modules over some ring R. So this category has left modules over R as objects, module homomorphisms as morphisms, identity homomorphisms as the identity morphisms, and composition of homomorphisms as composition of morphisms. Next, let us talk about subcategories. Let C be a category. Definition: a subcategory D of C consists of a subclass D of objects in C, and then for each object I and j in D, a subset Dij inside the set of morphisms from I to j in C. And then this datum is supposed to satisfy the following axioms. First of all, D should contain the identity morphisms on all objects which belong to D. And then D should be closed with respect to composition of morphisms. So if we take two morphisms in D and we can compose them in C, then their composition must belong to D. Here are some types of subcategories. A subcategory D of C is called full, provided that Dij is equal to Cij for all objects I and j in D. In other words, a full subcategory is completely determined by the objects it contains. As soon as it contains two objects, it must contain all morphisms between them in all directions. Here are some examples. We saw already one example. The category of abelian groups is a full subcategory of the category of groups. Second example, the category of finite sets is a full subcategory of sets. Next example, for ring R, the category of all R modules has as a full subcategory the category of all finitely generated R modules. Note that the category of all R modules is denoted by R mod with capital M, while the category of all finitely generated R modules is usually denoted by R mod with little m. Example 4, for a field K, we have the category of all finite dimensional vector spaces over K, and it is a full subcategory of the category of all vector spaces over K. Example 5, we have the category of finite sets, which is a full subcategory in the category of all sets, and this category of finite sets has a non-full subcategory, which is usually denoted by Fi, which has the same objects as the category of finite sets, but whose morphisms are all injective maps between finite sets. In particular, for the category Fi, there are no morphism from a set with 10 elements to a set with 5 elements, because there are no injective maps between such sets. And a kind of opposite example, example 6, the category of finite sets has a non-full subcategory, which is usually denoted by Fs, whose objects are all finite sets, and morphisms are all surjective maps between finite sets. Now let us define the notion of an opposite category. Let C be a category. We define the opposite category COP as follows. It has the same objects as the original category C. For two objects ij, we define the set of morphisms in the opposite category from I to j as the set consisting of the expressions Fop, where F is a morphism in C from j to I. So we take all morphisms in C from j to I and put a decoration op on them. The identity morphisms in the opposite category are exactly the identity morphisms in the original category with a decoration op, and the composition is defined as follows. If we compose Fop with Gop, so Fop after Gop, we should compose G after F and then take op. So that's the definition. In other words, the opposite category is obtained from C by reversing all morphisms. And sometimes one calls morphisms in a category by arrows. So here is an illustration. So if in the original category C, we have a morphism F from I to J and a morphism G from J to K, then we have the composition G after F, which is a morphism from I to K. Then in COP, we will have the morphism Fop from J to I and the morphism Gop from K to J. We can compose them, so Fop after Gop, and by definition, this composition is equal to the opposite of the composition G after F. So this is the definition of an opposite category. Now let us talk about morphisms between categories. So homomorphisms of categories are called functors. Here is a formal definition. Let C and D be two categories. A functor f from C to D consists of the following data. First of all, we have a function from the class of objects of C to the class of objects of D. And then, for each pair ij of objects in C, we have a function f, which depends on ij, of course, from the set Cij to the set D of f of I, f of j. So to any morphism from I to j in C, we put into correspondence a morphism from f of I to f of j in D. And this datum is supposed to be subject to the following axioms. First of all, each functor sends the identity morphism at I to the identity morphism at f of I for all objects I in C. Second, if we apply the functor to the composition beta after alpha of two morphisms, the outcome should be equal to the composition of f of beta and f of alpha. And this should be okay for all ijk in C, for all alpha morphism from I to j in C, and for all beta a morphism from j to k in C. There are some special kinds of functors. So a functor f from C to D is called full, provided that each function fij, here from Cij to D f of I, f of j, if each such function is surjective. And the functor f is called faithful, provided that all these functions fij are injective. Here are some examples. Example 1, for each category C, we have the identity functor idc on C, which assigns to each object I in C this object I, and to each morphism alpha in C from I to j the same morphism alpha. Here is another example. For each subcategory D of the category C, there is an inclusion functor iota from D to C, which again assigns to each object I in D the same object I, now considered as the object of C, and to each morphism alpha in D from I to j the same morphism alpha, which is now considered as a morphism from I to j in C. Here's the third example. Let C be a category and I a fixed object in C. Then we have the so-called representable functor Ci blank, which starts in the category C and goes to the category of sets. And this functor assigns to each object j in C the set of all morphisms in C from I to j, so the set Cij, and to each morphism f from j to k in C, it assigns the function of composition with f after something, where the something is an element from Cij, and then the output of this function is a morphism in C from I to k. So the functors which we just discussed are called covariant functors. In other words, these are functors which preserve the direction of arrows. There are also the so-called contravariant functors from C to D, and these are formally defined as covariant functors from C op to D. In other words, a contravariant functor is a functor which reverses directions of arrows. And for convenience, if one speaks about contravariant functors, then one removes the decoration op on arrows. So here is a nice example. If C is a category and I is a fixed object in C, then we have the representable contravariant functor C blank I, which starts from the category C and goes to the category of sets. So this functor assigns to an object j in C the set of all morphisms in C from j to I, and it assigns to a morphism f in C from j to k the function of composition of f before something, where the something is taken from cky, and then this function goes to cji. Next, let us talk about congruences on categories. Let C be a category. Definition: a congruence tilde on C is a collection of equivalence relations tilde ij on each Cij such that for all morphisms G and H from I to J and all morphisms F from J to K, the fact that G is tilde equivalent to H implies that F after G is tilde equivalent to F after H. And similarly on the other side, for all morphisms G and H from I to J, and for any morphism F from K to I, the fact that G is tilde equivalent to H implies that G after F should be tilde equivalent to H after F. And of course, one usually simply writes tilde instead of tilde ij and so on. For example, one trivial congruence would be given by the equality relations. So if we take all tilde ij's to be just the equality relations, this obviously defines a congruence. And another trivial example, we can also take tilde to be the full relation. So tilde ij is a full relation on Cij for all I and j. And of course, this also trivially defines a congruence. And we can intersect congruences, and we take the minimal congruence, which contains two given congruences. So all congruences on a category form a lattice with respect to inclusions. And the first congruence given by the equality relations is the minimal element in this lattice. And the second congruence given by full relations is the maximum element in this lattice. Now we can define quotients of categories. So let C be a category, and let tilde be a congruence on C. We can define the quotient category C modulo tilde as follows. This category has exactly the same objects in C, and for two objects I and j, we define the morphism space from I to j in this quotient category as the quotient of Cij modulo tilde ij, modulo the equivalence relation on this set. So we define the identity morphisms in the quotient as the class, as the equivalence class, which contains the original identity morphism in C. And we define composition in this quotient category by inducing it from the composition in the category C. So this means that if we want to compose two equivalence classes, we pick two representatives, one in each class, and compose them. So the composition is defined if and only if the representatives can be composed, and then we compose the representatives and pick the equivalence class which contains that composition. One needs to show, of course, that this is well defined because we define things on sets by picking representatives, but this can be proved similarly to semigroups using the congruence axioms. The congruence axioms are exactly the things which you need in order to prove that this is well defined. And so we can talk in this way about quotients of categories. Next, a very special thing about categories is that in categories we can speak about isomorphic objects. So let C be a category. Definition: two objects I and j in C are called isomorphic. It's denoted I is isomorphic to j, provided that there exists a morphism F in C from I to j and a morphism G in C from j to I, such that the composition of G after F is equal to the identity on I, and the composition of F after G is equal to the identity on J. Example 1. In the category sets, two objects X and Y are isomorphic if and only if they have the same cardinality. Example 2. In the category of all finite-dimensional vector spaces over K, two objects are isomorphic if and only if they have the same dimension. This follows directly from linear algebra. Example 3, which is directly related to our course, let R be a principal ideal domain. Then, in the category of all finitely generated R modules, two objects are isomorphic if and only if they have the same canonical decomposition, which we defined and studied in the second part of this course. And one more definition, which will be necessary later. A functor f from C to D is called dense, or essentially surjective, provided that for any object j in D, there is an object I in C such that j is isomorphic to f of I. So in some sense, one can say that the image of f hits all isomorphism classes of objects in the target category. Now we can talk about composition of functors. Let B, C, and D be categories. Let F be a functor from B to C, and G a functor from C to D. Then we can define the composition of G after F, which will be a functor from B to D, as follows. If you have an object I in B, then this composition applied to I is by definition equal to G applied to F of I. And if we have a morphism H in B from I to J, then this composition applied to H is equal to G of F of H, and this will be a morphism in D from G of F of I to G of F of J. And it is easy to check that this composition is a functor, and it's called the composition of the functors F and G. It is also easy to check that composition of functors is associative, and that the identity functors have the unitality property with respect to this composition. So this naturally leads to the notion of the category of categories. So now we can define the category cat as follows. The objects of cat are categories. Morphisms in this category are functors. Identity morphisms are identity functors. And composition in this category is just composition of functors. In particular, we have the notion of isomorphic categories. Two categories C and D are isomorphic, provided that there are functors F from C to D and G from D to C, such that the composition of G after F is equal to the identity functor on C, and the composition of F after G is equal to the identity functor on D. We will see in the coming lectures that this notion is way too restrictive in the context of categories, and a much weaker notion, which is the notion of equivalence of categories, is much more useful in this context. Okay, some problems and questions at the end. Question 1. Explain why monoids are essentially the same things as categories with one object. Question 2. Define with all details the category of binary relations, that is, the category whose objects are sets and morphisms are binary relations between sets. Question 3. Check with all details that G composed with F is a functor, if G and F are functors. Question 4. Check with all details that composition of functors is associative. And question 5. Check with all details that identity functors are unital with respect to composition of functors. Thank you very much, and see you next time.